So today, I'd like to talk about the computational material design. Material design methodologies, some examples including thorium and indium compound, and 112 family ion-based superconductor. So through this example, I emphasize how two different types of correlation, static and dynamic correlation, affect the material design process. So first example is for the static correlation, and the second one is for the dynamic correlation. Okay, the material design, especially in the correlated material system, has been led by experiment. At first, experimentalists try to find a new material and measure its physical property. And then theorists provide the physical explanation. So historically, the material discovery has proceeded by trial and error or by accident. So for example, these materials were discovered by chance. But however, the new paradigm is realized in material design. So material design not only explains the experimental data, but also predict new interesting materials. So in able to find new interesting material and test and develop a material design methodology. And also it finally can improve our physical understanding from material discovery. So there are many accomplishments in theory-guided material design. So Hafnium hafnium antimonide, which is not reported in ICSD database, and also the iron O2 at high pressure. So all of these materials were proposed theoretically at first time, and then experiment confirm this theory. So this figure shows how many crystal structures discovered by year. So as you can see, the number is increasing rapidly from 1960. So this figure shows the increasing interest in the material design. Okay, this figure shows the computational material design workflow. At first, the material design starts from the qualitative idea. So it includes the material concept. So from our physical or chemical intuition, we propose a new interesting material expected to show good physical property. Then the next step is the electron structure calculation. So in this step, we use the DFT method in order to check our initial intuition is promising or not. So if it is, we do the crystal structure prediction by using the global optimization, such as evolutionary algorithm. So once we find a crystal structure, then we check whether the material is thermodynamically stable or not. So in this step, we need a database because we have to check the stability against the decomposition into all other substances in the chemical system. So if we find a stable compound, then we do the electron structure calculation again with more elaborated methods such as DFT plus Godzilla or DFT plus TMFT method. So these many-body methods enable to study the physical property more precisely. So this step enables to provide another qualitative idea. So the computational workflow shows the cyclic process. So the electron structure calculation shows the structure to property, and the crystal structure prediction shows composition to structure, and the global stability shows the chemical system to composition. So the time is limited. I'd like to focus on the global stability in this talk. So there are two main issues in the global stability. The first one is the computational DFT error, and the second one is no many-body database is available. So we will discuss item by item. So first issue is that there is computational error in the DFT calculation. So in order to resolve this issue, we need an empirical correction. So these figures show the computational error in DFT GGA formation energy. In the left-hand side figure, the x-axis shows the energy difference between the GGA and experimental formation energy, that is the computational error, and the y-axis shows the number of compounds. So as you can see, for mode of compound, DRT shows significant error. So this error is clearly shown in the right-hand side figure. So here, the x-axis shows the GGA formation energy, and the y-axis shows the experimental formation energy. And here, the black solid line exhibits the perfect match between the theory and experiment. So again, the computations are away from the perfect match line. So it indicates that we need the empirical correction in the DRT formation energy. Then the following question could arise naturally. So does inclusion of on-site Coulomb mu, so-called GJ plus U, improve the DRT error? So these following figures give an answer. So left-hand side figure shows the GJ calculation, and the right-hand side figure shows GJ plus U calculation. So GJ plus U calculation still has significant deviation from the perfect match line. So inclusion U is not enough. So we need empirical correction further. So there are three broadly used empirical schemes for correction. The first one is the fitted elemental phase reference energy, simply called FARE. And the second one is material project. And the third one is the open quantum material database scheme. So we do not have enough time. I skip the detail. So if you want to know detail, I explain later. So before the empirical correction, the distribution of the computational error looked like this. However, after the empirical correction, the distribution is improved so much, and the mean value of the distribution is almost consistent with the black solid line. So here we use the material project empirical scheme. So another empirical scheme called FARE also gives the good statistic. So both empirical schemes reduce the systematic error realized in the DRT computation. However, they are still significant standard deviation. So due to the sizable deviation, a compound predicted to be stable will not necessarily be found in experiment and vice versa. Then our question is, how can we provide a reliable result for the global stability? So we will discuss in this slide. So for simplicity, I'd like to consider the binary compound, which is not listed in the ICSD database and also is not studied yet in experiment. So in this case, the experimental formation energy is not acceptable. Then what can we do is that we estimate the formation energy theoretically. So it is possible because the formation energy is the energy difference between after and before the chemical reaction. So there are two ways to go. The first one is, if you have the exact method, then we can use it to obtain the exact formation energy. So when the exact formation energy is smaller than 0, this condition guarantees that experimental formation energy is smaller than 0. So it means that the material will be synthesized in experiment 100%. However, the problem is that we do not have the exact method. So the alternative way is that we estimate the formation energy within the DRT method along with the empirical correction. However, due to the DRT error, as shown before, the DRT formation energy smaller than 0 does not guarantee that the negative experimental formation energy. Then our question is, what is probability of negative experimental formation energy given that DRT formation energy has some certain value of X? So in order to the possibility, we do the following procedure. So first, we merge our existing database and estimate the computational error. And we realized that the computational error follows the probability density function like this form. So by using the regression analysis, we obtain the parameter alpha, beta, mu in this formula, and then we obtain the analytical form of the probability density function. Then the next step is we estimate probability that experimental formation energy is smaller than 0. So we call this probability as the existence probability. So therefore, the existence probability Px is the probability that experimental formation energy is smaller than 0, given that the DFT formation energy has a certain value of x. So we set the experimental value as y and integrate from -infinity to 0 with respect to value of y. Then the experimental value has y value and the calculation value has x value. So in this case, the computational error is simply x minus y. And we already know that the computational error x minus y follows the probability density function. So we can simply change the probability into the probability density function. And from the calculation, we can estimate the existence probability for certain value of x. Then the final step is that we test with experiment. So if our new proposed material is synthesized in experiment, it indicates that the probability, existence probability would be high. So if it is, the existence probability provide a reliable result for the global stability. So we obtained the existence probability for two different empirical collections, Barrett and the material project, as a function of the computed formation energy. So two schemes give almost similar behavior. So again, the existence probability is a probability for a compound to exist. So for example, if you propose a new material and want to know whether the compound could be synthesized in experiment, the existence probability gives the information. So therefore, it is a good indicator for material design. Okay, the second issue in the global stability is that currently the DFT formation energy are only available in the material database. So in order to do the reliable material design for the strongly correlated electron system, the Godzilla or DMFT database is necessary. So the Barcoso is a good example. So DFT formation energy with empirical collection gives the positive value. It means that Barcoso is not thermodynamically stable. The corresponding existence probability is 0.17. It is small, and it means that it is not likely to exist in experiment. However, in the previous talk, Megan mentioned that the Barcoso is eventually synthesized in experiment. And also in 2016, Oxford chemistry group reported that they successfully synthesized this material in experiment. So this finding encourages us to check the global stability more thoroughly. So we found that the formation energy computed within the Godzilla energy gives a negative value. It means that Barcoso is stable. So it is consistent with the experiment. So the Godzilla method gives a more reliable result than the DFT one. We checked the Godzilla formation energy for some other correlated material. So first two materials are lanthan copper sulfur oxide compound. So again, in the previous talk, Megan mentioned that these two materials are not stable and decompose into other substances. So both DFT and Godzilla describe the unstable phase, which is consistent with the experiment. And the third material is a new mercury-based cuprous superconductor, which is not reported in ICSD database. So interesting point is that the DRP described the unstable base. However, the Godzilla described the stable base. So we expect that this new mercury-based Q+ superconductor could be synthesized in experiment. So here, I'd like to emphasize that the Godzilla and DMFT database would provide better statistics and more reliable computational results, especially in strongly correlated electronic systems. Okay, so if you have the many-body database, then the distribution of the error, computational error, close to the data function, and the existence probability become a step function. So it could show the important aspect of dynamic correlation in the material design process. Okay, so far I briefly introduced the material design methodology. So now I'd like to give a specific example of material design. The first example is the volume and indium compound, which are related to barium bismuth oxide compounds. So in this example, I emphasize the impact of static correlation. Okay, so 1988, the potassium doped barium bismuth oxide was reported to show the superconductivity with transition temperature about 30 Kelvin. So electron proton coupling constant lambda was estimated to be 0.33 in the ADA method. However, it is too small to explain the observed transition temperature. So two different groups estimated the lambda within the HSE hybrid functional or GW method and found that the lambda is nearly 1. So it can explain the observed transition temperature. So it means that the static correlation here, the non-local correlation enhances the lambda by a factor of 3. So this idea was confirmed by the recent RPES experiment. So here, the empty triangle corresponds to the band dispersion measured by RPES experiment. And as you can see, the RPES data quite well match with the HSE band calculation. So from this calculation, we try to find a new type of superconductor like barium bismuth oxide. It is our motivation to do the material design. So the first target materials are the thallium compound, which are not reported in ICSD database. So theory proposed that the older compound show quite large transition temperature, 30 and 21 Kelvin. So these compounds are successfully synthesized in experiment. And in experiment, the band gap is reduced upon pressure. It indicates that the pressure derived the metallicity in this compound. However, attempt to dope was not successful and the superconductivity was not observed in experiment. So our second target material are indium compound. So indium is located just above thallium in the periodic table. So we expect that the indium compounds show the similar superconducting behavior. And besides, the indium compounds do not have the toxicity problem, so they can be easily synthesized in experiment. So we applied the evolutionary algorithm and found that these crystal structure or possible candidate structure. And all of them have nearly degenerate energy, so the multiple degenerate bases could be available. And also metastable space is possible. So from this observation, we can say we can predict new material with high confidence. However, we predict crystal structure with less confidence. So from the material design, we found that the cesium indium chloride, which is not reported in ICSD database, it is thermodynamically stable, and it has the existence probability of 0.52. It is quite sizable. And this compound is successfully synthesized in experiment, and the experimental space group has the IPOM tetragonal structure. The computation also predict that the IPOM is the possible candidate structure. However, both of them is not same. we computed their total energy and found that the theoretically proposed ipoham has lower energy than the experimental one. So we found that the experimental crystal is a metastable base. Okay, we also found the stable indium compound that showed the superconductivity. It is the hold-off cesium indium fluoride. The estimated existence probability is 0.78. It is quite sizable. And the computed the superconducting transition temperature is about 24 Kelvin. So this result encouraged the pursuit of experimental synthesis. Okay, the second example is the 1-on-2 family ion-based superconductor. So unlike the first example, I emphasize the impact of dynamic correlation. So 1-on-2 family ion-based superconductor was predicted theoretically in 2009 at the first time. So the idea is that a simple substitution of arsenic for oxygen is available in 1,1,1 compound, then the hypothetical tetragonal 1-on-2 compound could be obtained. So from the DFT calculation, we also found that it had the metallic spatial layer. It is quite unique because the other ion-based superconductors have insulating layer. So our question is that the metallic layer affect the superconductivity? If it does, then the mechanism of the superconductivity is related to the charge fluctuation. And otherwise, it supports the spin fluctuation mechanism. So this is our motivation to do the material design in the 1-on-2 compound. Okay, we applied the evolutionary algorithm and found that the 1-on-2 compound has the monoclinic structure rather than the tetragonal one. So this structure is consistent with the experiment. So both structure possess the zigzag arsenic chain and also arsenic ion arsenic layer. So it indicates that evolutionary algorithm provide a correct crystal structure. Then the next step, we check the global stability of calcium ion arsenic tube. So DFT formation energy with empirical correction give a positive value of 13 MeV per atom, which means that the 1-on-2 compound is not stable. However, the existence probability is 0.39, which is still sizable. So it indicates that there's some possibility to exist. And Godzilla formation energy gives us somewhat smaller positive value of 7 MeV per atom. So the Godzilla describes more stable base than DFT results. We also checked the Weyer's doping case and found that it induced the further stabilization. So this result explains why undoped 1-on-2 compound is not synthesized yet, and only Weyer's doping 1-on-2 compounds are synthesized in experiment. And we did the DMFT calculation and found that the arsenic spatial layer showed the metallic Dirac-like dispersion near the family level. So this behavior was confirmed by the RPS measurement. So both theory and experiment quite well match each other. In the right-hand side figure, it shows the transition temperature versus anion height in the whole family of ion-based superconductor. So as you can see, 1-on-2 data display the similar trend as the other ion-based superconductor. So it means that the metallic spatial layer in 1-on-2 compound does not affect the superconductivity. So it supports the spin fluctuation mediated superconductivity. So this example could show that even though we do not understand the mechanism of superconductivity, we can use the material design to test the current theory. So I'd like to emphasize once again that computational material design not only predict new interesting material, which is not reported in the ICSD database, but also can test the current theory in a research field that is less on the field. So before closing my talk, I appreciate my collaborators. In the theoretical side, the Gabi Trio and Adler and Turan Biller and Chokuri, I appreciate their collaboration. And in the experimental side, I appreciate the Master Greenblatt and Xiaoyan Tan. They had to make a material synthesize. So thank you for your attention.
Okay, so we're going to start with remote questions. Other questions here? Okay, so we're going to start with remote questions and then I'm going to ask.
Okay, yeah, thank you. Thank you for nice talk. I have a basic question. So regarding the distribution function for, I mean, x-axis is the difference of the energy and y-axis is the probability. So it seems that being independent from the specific schemes such as Ferre, material project, they show kind of universal distribution function. So my first question is, what is the line shape of the spectral function? And then is there a reason to have such kind of distribution? And okay, third question is, does the line shape, width or height, or its analytic shape, does it depend on the specific family of materials?
Okay, so the Ferre and material project has a common point. The common point is that instead of using GGA, the total energies are computed within the GGA plus U method. So you know the GGA underestimate the correlation. So GGA plus U improve some significant error with empirical correction. Yeah. The basic idea is that GGA is used instead of U, and some empirical correction give the best agreement between the experimental and the computational one.
Can you show the distribution function?
Yeah.
The one that was fitted with some formula.
So is it Lorentzian?
No, you had the formula.
Yeah.
Actually, it's right. So can you comment what the question is whether the distribution function, so you have all the materials.
Yeah.
The question was if it was Lorentzian. But you have the formula.
Okay, so actually, after the correction, the computational distribution looked like this, and we tried to fit this distribution with this certain type of probability function. Yeah. Then using the regression analysis, we realized that this distribution follows a certain type of form. Yeah.
So is it purely empirical?
Yeah.
Yeah.
Okay. Yeah. Thank you.
Marie, and then so in this DFT plus DNFT database that you plan to do, is there what is the double counting correction? Is there?
Well, it is a good question. So actually, we use the nominal double counting. So we believe that the nominal double counting is close to the exact double counting scheme. But actually, the Christian proposed the exact double counting scheme in the DMFT method. So now, we have the exact double counting scheme. Yeah. Yeah.
So thank you for the great talk. I really like the results. So I was wondering, you compared DFT with Kutzler formation energies. For any of these reactions, do you know what would happen if you spent the extra few $1,000s of computer time and do a DMFT calculation? does it give a result very similar to Kutzler?
Yeah, it's a good question. So our strategy is that the scan all the chemical reaction by the Godzilla is very time consuming. So our basic idea is that scan all possible chemical reaction by the DFT at first, and we assume that this chemical reaction doesn't change depend on which method we use. Then after we find the chemical reaction, we compute the Godzilla formation energy again, and we found that the Godzilla formation energy give a reliable result compared to the experimental data.
The question is whether you expect how accurate is the Godzilla. So the question is whether you would want to invest a lot more time.
Right.
And then you do the calculation.
Right. So in order to do that, we need to construct the Godzilla database. But you know, it's a very time-consuming one. Yeah.
Any other questions? If not, let's thank the speaker for a nice talk.